Good evening, everybody. I decided to do my video upload the night before on account of not doing one Friday and um, wanting to get this out early in case you guys are through the last few videos and want to kind of move ahead with the material. I did send you guys a couple of emails related to your next quiz, which you're going to take tomorrow. It's due by midnight. Same process that we've been doing for the last couple of them, um, which has worked great, except for me grading them takes forever. Um, this one, I sent you some instructions and some helpful tools and notes. So read the two emails that I sent you. They'll be really, really helpful. Basically, all you're going to do is write two APA style statements based on some tests that I ran for you in SPSS. And I sent you an email about which problems in the book they relate to. It's number 20 from chapter 11, and I believe number 23 from chapter 10, 23 or 24. Let me just turn around and I'll know it when I see it. 24, number 24. So the reason you need to know the problems is because in writing the APA style statements, you're going to have to write about how the variables relate to each other, and there's no way to, do that without reading the problem. But you're not going to have to actually do anything with the numbers from the problem. I did all that for you. You're welcome. So what we're going to talk about in this video is the first half-ish of chapter 12. Mostly the theoretical portion of chapter 12. I think I'm not going to walk you through any actual math. Again, I said without doing SPSS, it's going to be very, very difficult for us to be doing much math. I can't really do an ANOVA on the whiteboard behind me. I mean, I could. I'm just not going to have enough space. And frankly, it's going to fall on deaf ears. I think it's going to be a great way to bore you guys. Instead, what I will do is show you how ANOVA works and why we use ANOVA. Including defining ANOVA, because I probably haven't done that for you guys yet. So, sorry about the evening upload. Obviously, in my pajamas, but school spirit, right? Fun fact about this hoodie, it's from 2003. I got this when I was a junior in high school, and I've had it ever since. That was around the time that I committed myself to going to TCNJ. So, figured you guys would appreciate that. So we're going to be looking at the chapter 12 notes in the PowerPoint, so refer to that if you want to open it up. I would do that. I'm going to probably go up until we hit post hoc tests, and then I'll leave that for the next video, which I'll probably actually upload tomorrow night. I'm only doing the two lectures so close together in time because I didn't really get one up Friday, and I want to make sure that we're roughly staying on track. We don't have a lot of material left to go through. We have chapter 12 and maybe half of chapter 13, and that's it. With a short overview of effect size before you guys are ready for your second exam and your final exam, right? And then there's that project that I was telling you about, this mini project, which is not going to take a long time. So think about this quiz that you're working on tomorrow. Write down how long it takes you. This project will probably take you 2 to 3 times as long. So if this takes you 15 minutes, that'll take you about 30 to 45 minutes. And it's worth, a handful of quizzes essentially in terms of points. So it's not like anything major. Your long-term focus should be on your second exam, which will be the first or second week of May. So we have some time. And then your final exam, which will be due on the day of your final exam. And I'll try and be flexible about that due date. But by then, we're going to be done with material, so I can handhold you guys through all that stuff. Because I know some of this stuff feels kind of rushed and other things feel a little bit belabored. So I want to find a happy middle so, I can start helping you guys directly with some of those things. So anyway, the theoretical stuff from chapter 12 is really, really important to a broader understanding of how statistics works, of how experimental design works. Because ANOVA, or analysis of variance, is probably the most common statistical approach used in the sciences, if not definitely the social sciences. And there's different types of ANOVA. So one of the things the PowerPoint does is walks you through the different types through chapters 12 and 13. They're both ANOVA chapters. But the first ANOVA that we're going to consider is the one-way ANOVA, and that's going to be like our poster child of what an ANOVA is, and then we're going to build off of that. So before I get into the slides, I want to kind of bring back that mental flow chart that I had you guys create about statistical tests and when to use them. So remember, we said if you have one sample of data and a point of comparison that you wanted to compare it to, you had two options. You had the single sample Z test, right, our chapter 8 test, and your single sample T test. Okay? Now, your single sample Z test was used when you knew the population standard deviation and mean. The single sample T test you used when you didn't know those things. So that's the thing that separates them on the flowchart, right? Okay, now what happens when you have two samples of data? Okay, well now you have an additional question to ask. The question to ask is, are these samples, are these groups dependent or independent? Are they the same individuals assessed twice, or are they different people? If they're the same people, assessed at two different time points or two levels, under two conditions, what have you, then you use your dependent sample t-test. That's your chapter 11 test. Okay? If they are separate groups of people, they're independent, the between subject design, then you use your independent sample t-test. Okay, so those are the four tests that we've learned thus far. Correlations kind of sit aside as they're not the same kind of hypothesis test. Okay, so this kind of begs an interesting question. What do you do when you have more than two groups or more than two levels? Okay, more than two conditions that you want to assess. Okay, so a simple two-group design isn't going to work. What if you have to have 3 or 4 or 5 or 6 groups? How do you analyze that, right? So the way we do it is with analysis of variance. Now that particular scenario that I highlighted is good for a one-way ANOVA, right? So you have the same question to answer in terms of, are my groups made up of independent samples or dependent samples? If they're independent samples, great. You can use the one-way ANOVA approach that I'm going to kind of lay out for you guys today. If they're dependent, then you're going to use what's called a repeated measures ANOVA, which is still a one-way ANOVA. It just breaks it down typically over time or across a group of conditions. Works mathematically more or less the same way. Neither of these are t-tests. The way they assess the effect of an independent variable is different than the way a t-test does it. Okay? A t-test is a comparison of means. You take two means, put them over a standard error of the mean, some expected difference if there was no change, and then you use that as a basis for making a claim about whether one variable affected another. A ANOVA works differently, and I'll walk you through how it works. I'm doing this without the PowerPoint, so I want to just go into the PowerPoint. So one popular question that I tend to get, it's actually the first slide in the PowerPoint, so I'm glad I preempted it, is, well, okay, if you have three groups and they're independent, so three separate groups of individuals, like let's say you're, I don't know, let's say you're looking at the income levels of people who identify as Democrats or Republicans or independents. Three groups of people. An independent sample t-test can't handle that, at least not one. Why don't you just do multiple independent sample t-tests? Why don't you compare the Democrats to the Republicans first, then the Democrats to the independents, and then the Republicans to the independents? So it's essentially accomplish the same thing with three t-tests. That can work in certain scenarios. And actually, in the second video that I'm going to make, I will outline a way that that can work. That's actually kind of similar to the contrast approach to doing this. The issue there is going to be related to your type 1 error, okay? Because remember, every statistical test that you run carries with it a type 1 error rate that's equivalent to your alpha value. So if you set an alpha value of 0.05 for each of those three tests, then your experiment-wide alpha value goes up by, not exactly, but approximately 0.05 for every test that you run. It's not actually a linear relationship. So it would come in slightly under 0.15, okay? Which means the more of those tests you run, the higher the likelihood that one of them is going to contain a type 1 error, which is an issue. I mean, we talked in Chapter 8 pretty extensively about why type 1 error is something we want to avoid. Okay, so we have to come up with a different approach. So we'll talk about mathematically how ANOVA works and how it accomplishes what it does. Okay, so that relates to slides 2 and 3 about why not multiple t-tests. That kind of walks you through it. So I'm going to skip ahead and then backtrack. So if you go to slide 7, I lay out the different types of ANOVAs. Okay, because the reason I'm doing this now is because I want to extend that flow chart we were talking about to give you guys a better frame of reference of where we're going. So if you have more than 2 levels of an independent variable that you're interested in, and they're independent levels, separate groups of individuals are going to represent these levels in your experiment. You can do the one-way ANOVA as you're going to learn today, the between subjects one-way ANOVA. If they're within subjects, your levels, that is, they're within subjects, then you do a repeated measures ANOVA. Okay. Now there's one more extension to this flowchart. Actually, there's many more extensions to this flowchart if you're talking about the whole of statistics. But for the purposes of this class, there's another extension. What do you do if you have more than one independent variable? We haven't done that yet. Nothing like it. We've had multiple levels of one IV, but what if we added another IV? So thinking back to what I said, let's say we were looking at income levels for Democrats, Republicans, and independents, but we wanted to throw in another variable in there, and that's education level, and see how those IVs interact to produce changes in potential income. Could do it, right? But that's 2 IVs and how they affect a DV. That's something we'll talk about in chapter 13. That won't be on your final exam, but it will be on your second exam. So we'll get to that probably next week in the last series of uploads. So those are the 3 ANOVAs we're going to kind of cover. Now I'm actually going to, at least as far as a lot of the math goes, I'm going to punt on repeated measures ANOVA, only because I don't think we're going to get to it time-wise. But I mean, show you how it works. It's in the notes. You're going to read chapter 13, so feel free to read all that and take it in. I'm just not going to assess you guys on that. So those are the 3 ANOVAs that the book covers. Now, there is actually another extension to that branch beyond the 2-way ANOVA. It's possible that you have an ANOVA with multiple independent variables. It doesn't just have to be 2. You can have 3, 4. They're called factorial designs. And if you've ever seen a design represented, like this in the literature, we did a 2 by 2 by 3 ANOVA. What does that mean, right? Well, what it means is you had one independent variable with 2 levels, another one with 2 levels, and a third one with 3 levels. Okay? So if you're doing this using separate groups, you would need 2 times 2 is 4 times 3 is 12 groups to execute said design. Okay? It's also possible that some of these, in ANOVA speak, we refer to independent variables as factors. I'll remind you of that in a couple minutes because we're going to go through those slides. It's possible that some of these factors are either between subject or within subject. I mean, you could have between subject, within subject. You could do that. You can mix and match. Multifactorial designs like this, I think, are a little bit beyond the scope of this course. But if you take a class in multivariate stat, you'll cover these pretty extensively. So I did want to lay that out there for you as another option. And in fact, depending on the research that you're looking at, you'll see complex multifactorial designs like this. They're not uncommon. I think they tend to be the most common in the branches of psychology that vibrate more towards the social side. I mean, that's probably I don't know if that's an overgeneralization. I mean, you certainly saw them in neuroscience. It's not like they don't occur. So anyway, that kind of covers what's on slide 7. I want to do backtrack, though, to some ANOVA theory. Okay, so what ANOVA seeks to do is determine whether 3 or more means representing those levels. So if you have 4 groups, then you have 4 levels, you have 4 means, right? Are different from each other. Okay. Really, what you're looking for is to see if one of them is different. Now, how does ANOVA do this? I already kind of said that ANOVA doesn't compare means directly, anyway. ANOVA's hypotheses are written in terms of the means, right? So, like the way you would write your null hypothesis for a one-way ANOVA if you had three groups is like this: mean 1 equals mean 2 equals mean 3. Or you could just say all means are equal. Okay? Your alternative has to be not all means are equal. And the reason for that is because any one of these equal signs swapped for a non-equal sign would satisfy the conditions of the alternative hypothesis, right? So think about this for a second. Let's say you don't have three groups. Let's say you have 9 groups, okay? Your null is that they're all equal to each other. Not one of them stands apart as any different. If you had to write every possible outcome for your alternative that would satisfy the alternative, you don't want to do that. Write it out in plain English, or at least understand it in plain English. Again, I think we're past the point where I'm going to make you guys write out your null and alternative. But I do want you to understand what the test is trying to tell you. Okay, so what we're going to do now is kind of establish how ANOVA mathematically demonstrates that either all of your means are equal or not all of your means are equal. Okay, it doesn't do it the way you think it does in terms of how a t-test might approach it. Right, so again, back to those definitions then. I want to just make sure that we understand them. So on the 5th slide, you'll see the word factors, right? So using ANOVA speak, a factor is an independent variable. So up there in my multifactorial design, I actually have 3 factors. Okay, 1, 2, 3. Each one of those represents a factor. In a one-way ANOVA, what makes it a one-way ANOVA is you have one factor. That's it, one factor with at least 3 levels. Why at least 3 levels? Well, if you had 2 levels, you wouldn't really be doing a one-way ANOVA. You'd be doing an independent sample t-test, right? You'd have 2 groups and you could just compare them that way. But if you have more than 2 groups, you need to use the one-way ANOVA. So if I use the word factor, know that I'm using it interchangeably with independent variable. In this context, they mean the same thing. Not all contexts, but in this context, they mean the same thing. A level is a group within a factor, right? So levels and groups sometimes used interchangeably. In the case of the 3 political parties, or the 3 ways that you can register as part of a political party, I guess, we had 3 levels, right? We had Republicans, we had Democrats, we had independents. Okay. Each one of those represents a level. If you added another party, you would have 4 levels. Okay, so that's what it means. So when I say you need to have at least 3 levels to do a one-way ANOVA, I'm referring to the number of groups that you have. So pretty straightforward. Those are 2 big definitions to get out of the way. If you go about reading the chapter and you didn't kind of process those 2 definitions, you'd have a hard time because they're going to use factor and level all the time. So, okay. So, we're going to be considering the single factor design. This is on slide 8, which is our one-way ANOVA. It's the most straightforward ANOVA, and for that reason, I think it displays how ANOVA works the most efficiently, right? So I pointed out to you that your hypotheses are written as follows for the one-way ANOVA because that's what the test attempts to do, right? The test tends to demonstrate that all of your means are equal or they're not all equal. And you write them the same way every time, right? I mean, for every example, you're going to write them the exact same way. ANOVAs are also, we haven't really talked much about the F distribution, but the F distribution is a little bit like the chi-square distribution in that it is a one-tailed distribution. Okay, it is a distribution that starts at 1 and goes all the way towards positive infinity. And you'll see why in a minute. You can't actually produce a negative F statistic the same way you can produce a negative T statistic or a negative R statistic, right? And there's a really simple reason for this that you're going to come to understand. And once you see how the ANOVA works, many of you will be like, oh, that makes sense. Okay. So how do we go about actually analyzing variance? ANOVA stands for analysis of variance. So how do we do that? So what ANOVA seeks to do, and I'm not going, like I said, I'm not going to really walk you guys through much of the math, um, because the math that produces the numbers that you really need to kind of pour into the pot to get the ANOVA is all about sums of squares. It's all about calculating sums of squares. And not just one type of sums of squares, there's actually two types of sums of squares. And that actually speaks to how ANOVA works. So what ANOVA does is it looks at all of the variance in your entire test, right? Think of it as a pie. And then what it does is it parses it apart mathematically into variance that's due to within subject factors and between subject factors. Now, think about this for a second. If you wanted to determine that there was a difference between groups as a result of those groups being part of a specific level, which of those types of variances would you want more of? Would you want more between subject variance, or would you want more within subject variance? Between subject variance, right? Because between subject variance or between group variance suggests that there is a difference from group to group. That's what's going to feed into your effect. That's what's going to produce your effect. Your within subject variance is your variance that occurs within each group. Okay? That you can treat or consider to be something like your random variability, the fact that the people in your sample are different and they're going to vary. Ideally, you want that level of variance to be as low as humanly possible, right? Because if it's not, it's going to blow up and wash away a lot of the variance that makes up your effect. So that's basically how it works. It partitions the variance in your sample into between subject variance and within subject variance. It does this mathematically. I'm not going to show you how, but what it does is it produces two different types of sums of squares. And we actually call them sums of squares between and sums of squares within. Okay. If you want to see how they're calculated, the equation is in the slide and it's definitely in the book. Not going to walk you through, again, the math. If you do the ANOVA in SPSS, which next video I'll post a screen share of me doing it, and I'll kind of try to walk you guys through the anatomy of the output so you can see like, oh, okay, there's the main effect test, and there's the post hoc test, and here's my SS between, my SS within, so on and so forth. So I'll walk you guys through all that. Remember, we're not going to be doing much math in this video. So you start there. You take your total sums of squares in your data set, and you parse it into sums of squares between, sums of squares within, and actually, if you add those two things together, you get something called your sums of squares total, right? Those three things. Right? So in order to fully execute a one-way ANOVA, the main effect test, and I'll talk about what I mean by main effect in a minute, there's actually 9 calculations you need to perform, some of which are very easy. I'm going to show you how to do it in this video. Others, like the sums of squares ones, they're too long-winded for right now. If we were in person and in a classroom setting and I had a little bit of extra time, I could show you how it works. But for now, just consider the fact that they're calculated. So if you want to think of it this way, I stated this earlier in the video, but I'm going to restate it because I think slide 11 is a great way to understand this. So the t-test ratio tells you that t is the difference between two means over some expected level of error. Where does that expected level of error come from? Well, it comes from two sources, right? It comes from your standard error of the mean, but your standard error of the mean is a product of the standard deviation of your sample, so your inferred population standard deviation, over the square root of n. So your sample size also plays a role. Those two things conspire to give you a baseline level of variability by which you can compare two means to see if they're truly different. So you might have drastically different means, but if your expected level of error is high, it's going to wash out that difference, right? Or if your sample size is too small, it's going to produce a larger standard error of the mean and also wash out that difference. So this gets into issues of statistical power. The F ratio works a little bit differently. Your F ratio is a product of your variance between and your variance within. It's literally that. We don't really write variance between, variance within, at least I don't. Some textbooks will write it as s squared between over s squared within. There's actually another name that we use for that, and I'll substitute that out in a minute. But that's how it works. It's a simple ratio. Now, to the point about the F distribution starting at 1 and not being negative, ask yourself, I'm going to want you guys to think about this rhetorically, so pause me for a second and think about why it starts at 1 and can't be negative. Okay, now I'm going to tell you. It starts at 1 and can't be negative because they're based on variances, right? Variances are squared numbers. They can't be negative. They also can't be less than 1. Well, no, they can be less than 1, but in this case, this value will always be higher than this value because this value to some extent includes this value. So like 9 over 9 is acceptable here, 8 over 9 is not. Okay. If this number is 9, this number has to be 9 or more, which is why this number starts at 1, okay, and cannot be negative, right? So if you look at your F table in the back of your book, we're not going to play too much with it today, but I believe it's on page, oh, did they not give you, that's really lame if they don't give you the graph. Oh, they do give you the graph. 577. It's on 577. So you can see it starts at 1 and continues on. Okay, so there's that. Let's see. So the two types of variances story I kind of walked you through is on slide 12. So remember, when you conduct an ANOVA, you have two sources of variability: your variability within groups, which is actual error, if you want to think of it that way. Error isn't always a bad thing. It just means a difference between two things. That's your bad kind of error. And your variability between groups, or your variance between groups, that's treatment error. And that's the kind of error that you want if you're predicting an effect, right? You want there to be a lot of variability between groups. You don't want there to be a lot of variability within your groups, okay? Between them, yes, not within. Again, if you're predicting a difference between the two. So the F ratio simply ends up being a comparison of these two types of error. So on slide 13, it illustrates how this works. So if you were to start with, let's say I walked you through the entire ANOVA process and it works out that your variance between is 10 and your variance within was 9. Well, you guys don't need to be an expert in ANOVA to know that 10 over 9 is going to produce, what is it, 1.11? As a statistic, that's not really compelling. It's not going to be significant because most of your between subject variance is your within within group variance. You don't want that. That's not going to suggest to you that there's a difference between those groups, right? Now, if you were to hold that variance within constant at 9 and up your variance between to 45, well, 45 over 9 is a 5-fold difference between the two, and that produces an F statistic equaling 5. That's a little bit more compelling to say, yeah, there was an effect of this between subject factor, okay, whatever your IV happens to be. So what I'll say for you now is the same rules apply as any other statistic. What makes statistical significance? Well, once you select your alpha, you look up an F critical value, and if your F value exceeds that critical value, then you can reject your null hypothesis. What I will tell you as a general rule is that any F statistic that's appreciably different from 1 will often produce statistical significance. So, you have to look up a couple of different degrees of freedoms. ANOVA is a little bit different than what you guys are used to, so I'll walk you guys through all that too. I do want to just loop back really quickly to the hypotheses, however, because I want you to understand what the ANOVA is actually doing. So let's say you have 3 groups, and let's say you get a significant F statistic, and you reject your null hypothesis. What is your alternative state? Because that's what you're restating. Not all of my means are equal. Fantastic. Which one is different? You don't know that yet. You actually have to do additional tests to tease that apart. And that's what part 2 of this video is going to be about. later this week. They're called post hoc tests. What this test I'm talking about, the F test, or as they call it, the omnibus F test. Why is it omnibus? Latin omnibus means all things. Is because it tests all of the means at once and only has the ability to tell you if one of them, or at least one of them, is different. It doesn't tell you which one is different. You actually have to do targeted testing to figure that out, or multiple pairwise comparisons, which we'll get to, right? So we call this the main effect test, right? So the F test is a main effect test that simply tells you whether there's an effect of your IV. It doesn't characterize the effect of the IV, it doesn't tell you which groups are different, but it tells you that there's a general effect. So whenever you hear me use the phrase main effect, that's what I'm referring to, right? So this video, if you will, is kind of a build up to the main effect test. Next video will be a build up to post hoc testing and how that works. Right, so that's what we mean by main effect test. So there is some, not going to go through it too extensively, but there is some new notation to make note of. It's on slide 15. The notation is really useful for you if you're going to try to do this by hand, which you can do. Most of you guys will have the math ability to read the book and, essentially sit down and mess with it by hand. And I applaud you if you attempt to do that. Bear in mind, one of the reasons I don't do this and haven't with a class in some time is, while the math itself is not difficult, it's a lot of arithmetic, to be honest. It's a lot of repetitive arithmetic, which means it's very error prone. It's not uncommon to spend 10 to 15 minutes doing this test and to make a very, very small error in your mental math, and the results just aren't right, not even close. And you do it in SPSS and you're done in a heartbeat. So for my money, rely on technology. If you really want to foster a deeper understanding of how the test works, it's one of the reasons why I do have you guys do the math in some cases. By all means, go for it. I think you'll have a really good understanding of how ANOVA works if you attempt to do it this way, if you have time to burn. If you don't, we'll stick to doing it in SPSS. Okay. There is one, however, piece of new notation that I think will be useful for you guys no matter what, and that's K. Actually, K is not new. I've talked about K before, but K is the number of levels you have or number of groups you have. Okay, and there's a reason you'll need to know that in just a second. So the basic approach, though, this is the part that I think you guys are going to love, because most of what makes up the ANOVA is math that you're already familiar with. So real quick, how do we find a variance? Good. We take your sums of squares and you divide by your degrees of freedom. Awesome. So look at this. Here's the sums of squares. Here's the sums of squares. We're going to ignore this one for now. But if I have a degrees of freedom that goes with this, and degrees of freedom that goes with this, I can get from this to this, and then from this to this, just by dividing by degrees of freedom. So that's where those 9 calculations come from. So there's 3 calculations for your sums of squares, between, within, and total. There's 3 calculations for your degrees of freedom, between, within, and total. There's 2 calculations for your variance, between, within, and then there's your final F ratio, which is the 9th calculation. So the one piece of math that I am going to hold you guys responsible for is filling in an empty ANOVA table. And once you get this process, this is super easy, and honestly, it's easier than like the easiest Sudoku board you've ever done. But it is kind of like a little puzzle to be solved. So we're going to walk through those calculations now. So the calculations are on slide 17. So remember, you're going to have to calculate 3 different types of sums of squares, 3 different types of degrees of freedom, 2 different types of variance, and then lastly your final F ratio. And that's that. So the sums of squares formula are on slide 18. Again, with the new notation in there, if you guys wanted to attempt doing that, go for it. Once you get those sums of squares values, I'm going to show you what to do next. It's the sums of squares that we're not really going to be calculating, because that's where I think most of the arithmetic comes, and where it gets the trickiest. So, however, moving to slide 20, degrees of freedom you are going to calculate. So, a couple of things to note. So, in all cases, your between value plus your within value equals your total value. Same is true for degrees of freedom total. So if you know that rule, then you can kind of cheat a little bit. So your degrees of freedom total for any test, what is it? Well, it's the number of individuals you have minus 1. We've been using that degrees of freedom for all so on. So in other words, it's big N minus 1. This is all, again, by the way, on slide 20. So degrees of freedom total equals N minus 1, right? And that, I keep clicking away. Your degrees of freedom between is K minus 1. What's K? It's the number of levels you have. So in a 3-level design, it's 3 minus 1. So degrees of freedom between is K minus 1. I start with those two because if you're clever, the third one is a lot easier than it needs to be, because you can literally take this number and subtract it from this number, and that will give you degrees of freedom within. Or you can do N minus K. Big N minus K is the easiest way to do it. So within is big N minus K. So if you had 20, let's say you had 21 individuals broken up evenly into 3 groups, right? So you're going to have 7 people per group. That's 20 minus 3. That's 17. Is that right? Oh, my brain hurts. Hold on a minute. Oh, it's not 20, it's 21. That's why. I said 20 and then meant 21. It would be 18, right? So there's 2 ways to look at that. It's the total number of individuals you have minus the number of groups, so 21 minus 3, or little n minus 1 for each group, and then you add them together. So if you have 7 people per group, n minus 1 is 6, little n minus 1. 6 plus 6 plus 6 is 18. That's what was confusing me. I was like, how could that add up to 17? And then I forgot that I said 21. So yeah, there's that. So that's how you calculate your degrees of freedom. Now, the reason that's important is because your degrees of freedom has an effect on the general shape of your distribution, right? You have 2 different types of degrees of freedom here. You now have the number of groups that you have plus the number of total of individuals per group. So when you look up your values, your F critical value, that is, you need to use both of those degrees of freedoms to do it. On the left-hand side, you have your degrees of freedom for your denominator, which is within, and then you have it for your numerator along the top, which is between. You need to match those 2 up, and then the book only gives you 0.05 and 0.01. 0.05 is up there in normal font, and then 0.01 is in bold-faced. And if you need to look up a different value, you have to use a different table. Or SPSS will obviously give you your p-value directly if you're doing it that way. So that's how you calculate your degrees of freedom. So now, okay, you've probably got this in hand already. If I gave you sums of squares and I showed you how to calculate degrees of freedom, you could very easily calculate your variance between and your variance within. You would just take your sums of squares between, divide by your degrees of freedom between to get your variance between. Just like any other variance calculation, right? We've been doing this since chapter 4. Sums of squares divided by degrees of freedom get you variance, right? Sums of squares within divided by degrees of freedom within, variance within, right? So that's the next calculation that's coming. So if you go to slide 21, you will see that. Now, in ANOVA speak, or at least the way most of us were trained, we refer to variance between and variance within not as variance between and variance within, but as mean squared between and mean squared within. Why mean squared? Well, again, if you remember back to chapter 4, variances are mean squared values. Why are they a mean value? Well, because they're an average, where you use your degrees of freedom as the denominator. So that's the mean part, mean. And they're squared because they're still based on the squared step that you use to calculate sums of squares. You haven't taken the square root of them yet, so they're not standard deviations, they're squared values. So mean squared between, mean squared within. So I'll often refer to those as MSB and MSW. So that's variance between and variance within. I am 100% okay with you guys referring to them as variance between and variance within. In fact, I think this textbook does so. So that's completely your prerogative. I can promise you anybody who's literate in statistics will know what you're talking about, so no worries there. But that is your final F ratio. So like use your sums of squares and your degrees of freedom to produce those variances, take the ratio of those variances, there's your F statistic. That F statistic tells you if one of your means is different from the others. And then the real fun starts. So on slide 22, that is distilled for you. And again, there's that reminder on the bottom that your F value cannot be negative because it's based on variances. I can't promise you that that won't be a test question. Although now that it's open note, that would be kind of a softball, I think. Okay, so given all of that information, we can play a little game. And in fact, beyond slide 25 is probably where I'm going to stop. So what we'll do is now that we know all of that for the main effect test, I'm going to put up an incomplete ANOVA table on the board, and I'm going to walk you guys through it. It's actually not so bad, and most of you guys are going to find this kind of fun, I think. This is my favorite way to do quizzes for ANOVA, by the way, because I don't really have you do a lot of hand math, but you can fill in incomplete ANOVA tables, and that does indicate that you know how the ANOVA works, save for the sums of squares part. You have to give them the sums of squares, or at least some of them. So I'm going to pull one from chapter 12 that I like, put it on the board, and we'll do that, and that's how we'll wrap up, because I'm about 42 minutes, perfect. So trying to make these videos under 45 minutes, because otherwise they take an exponentially longer time to load for whatever reason. I think it's like a weird YouTube algorithm. Okay, so let's do number 16. So I'm going to read this to you. I'm going to construct an empty ANOVA table. Now, this is an ANOVA table that would be produced by a program like SPSS, where on this side you have, this says between, this says within, this says total, and then up here you have your sums of squares, your degrees of freedom, your mean squared, and then over here would be your F value. And then there's a blank for each one of these. So there's a number that goes here, there's a number that goes here, there's a number that goes here, 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 and here. Now, I could artfully choose to give you some of these numbers, and you would have no problem whatsoever filling this in just based on what I taught you. So let's try it. Number 16. The following summary table presents the results from an ANOVA comparing 3 treatment conditions, so K equals 3, with N equals 8 participants in each condition. So little n equals 8. So point of inference here, if you have 3 groups, each of those groups contains 8 individuals, your total sample size is 24. You're going to need that information to do this column. And this one tells you, hint, start with the degrees of freedom column. Yeah, it's probably the easiest way to approach it. And in this case, it's the only way to approach it, because the only numbers they give you in here are 93 and 15. And then you got to fill in the rest. But logically, this isn't that bad. So let's see. I'm going to start with degrees of freedom, and I'm just going to go right down the column. Now, there's one of these rows that you can complete in one shot if you do the degrees of freedom first, and that's this one, right? So remember, degrees of freedom for between is K minus 1. So this is 2. Now, remember the relationship at play here. Sums of squares divided by degrees of freedom equals variance, or mean squared. So in other words, this divided by this equals this. If you're working backwards, this times this equals this. So this has to be 30. Simple, right? Between plus within always equals total. So if this is 93 and this is 30, This has to be 63. Now I'm in a little bit of a quandary. I have to go back to the degrees of freedom column, otherwise I can't finish this out. So let me do total, degrees of freedom total first. So that's big N equals 24, big N minus 1 is total, so that's 23, which would make this 23 minus 2 is 21. Remember, these two will add up to each other. And then my mean squared, this divided by this, 63 divided by 21 is 3. 15 divided by 3 is 5. And we're done. That's it. Sorry, there's a little bit of a glare from my little chandelier. Oh, and that is not going away. Okay, so it's literally right across where it is. So let's see. There you go. Now you can see that it's 5, and this is 21. So, okay. Not used to doing these at night, so that the glare is a little bit more prominent, but. That's it. So practice with this, because if you understand how to do this, then you know how the math works, and it's really not that bad. A good one to take a stab at is 17. It's more or less the same thing. Not that there's a lot of real world applicability to doing this, so take my advice for what it's worth. But if you are going to do one of these, start with the degrees of freedom column, because as long as they give you the sample size and the number of groups there are, you can knock that column out right away and then use whatever other information they give you to do what I did and just reverse engineer the ANOVA. But remember, what you're basically looking at up here are 3 variance calculations with a ratio at the end. That is it. Actually, 2 variance calculations and then this. Really use the total row here to help you kind of figure out some of this other stuff. But that's it for tonight. Next video upload, I'm going to try and do tomorrow night. Full disclosure, though, tomorrow is my birthday, and my wife has something planned, although I don't know what she could possibly have planned. But, later on in the evening, I might record the second half of Chapter 12 and post it for you guys. Again, with the quiz posted, I don't want you guys to have to worry about watching this right away, so I'm not going to rush to get the next video out, but I want to have it up there in case if you are keeping up, you've got it up there and ready to go. I really want you guys to focus on the APA style statements though for now, and then later on in the week you can kind of come back to the ANOVA stuff, because again, we don't have a lot of material left to plow through. But shoot me any questions you have. I'll send you guys an email in a few letting you know that this is up. It's going to take me a while to upload it, but yeah, hope everybody's staying safe. Just so you know what's been going on in my world, unfortunately, Ashley and I had a COVID-19 death in our family. Her grandmother was in a nursing home in New Brunswick, so that's why this week was kind of a little bit, I was out of it. Mostly, I mean, I'm fine, but Ashley was a little bit, upset. So I kind of had to be the supportive husband and put some of my work on the back burner for this and for my main job. But she's okay now. It's the hardest part is obviously not being able to see her family, which I'm sure many of you guys are struggling with right now. Hopefully, hopefully everybody in your family is healthy and safe, and that's the most important thing for right now. What we're doing here is nice, but honestly, this is a distraction for the rest of what's going on, which is why I'm always happy to upload these videos and pretend that I'm actually talking to you guys. It's fun. Anyway, enough being morbid. Any condolences sent our way, we appreciate. I send my best wishes back to all of you guys, and I will see you in a day or two for the next part of Chapter 12. Have a great one, guys. Bye.